Hello, and welcome to another episode of Risky Business. I see here I got a shout out from SiFive for the interview. They spelled my username wrong, but that is okay. and We have some answers to our questions. So last time we were printing memory searching for Unix timestamps because uh, apparently the board ID is a Unix timestamp and we couldn't find it. And so Megan has the answer. She says that the addresses that we were looking at are in mask ROM, not OTP. The reason is that the OTP contents given in that table that we're looking at, um, they're offsets within the OTP, not absolute addresses. So the OTP region starts at this address here. So that's where we should look to find our ID. So that is interesting information. And I also posted a question. So you can see here, I posted a question about the output problem I have with my board. And Megan has an answer. She says she believes it's caused by the fact that the UART line is dropped low during reset on the SiFive 1, and the code is not waiting long enough to start sending on the UART after enabling it. So UART TX works with a single line which starts high, and then when the sender wants to send something, it pulls the line low to indicate a start bit. The receiver looks for the line going low as the start bit and then starts reading the bits that are sent by sampling periodically according to the baud rate or trying to detect the baud rate. If the TX line drops low, bounces around for some reason, such as during reset or while the GPIOs are being configured as the UART pins, the receiver might think it's a start bit, start interpreting junk as characters, and missing the real start bit and characters. So that's probably what the problem is that I'm having. And she says you could test this by putting a busy loop in the UART init function after the GPIOs have been configured for UART to give some time for the receiver to resynchronize and be ready to receive. You can see an example in LED fade demo, which is the demo that originally comes on the board. And it says, she says, it doesn't use the UART init function in init.c. So she provides a link here to the GitHub of the LED fade demo. And you can see right here, they do a busy loop. So they set a volatile int, and then they just loop for, what is this, like 10,000 iterations, where they just increment the variable. So it's volatile, so the compiler doesn't optimize it away. And then this busy loop just, spends some time incrementing a variable. And that allows it to wait a bit to avoid corruption on the UART. And this comment says, in some cases, switching to the IOF can lead to output glitches, so need to let the UART receiver timeout and resynchronize to the real start of the stream. So we're going to give that a try. So let me see here. Here's our demo, and I don't think I have the other stuff in the Freedom-E SDK open right now, so I'm going to take a moment and open all that stuff. So programming, Freedom-E SDK. I'm going to go into BSP since that's where we're mostly looking. Now I wonder if, here we go. Okay, so does this have what we want? It's got PLIC, encoding, platform, SiFive 1. Let's see what else we have. We're looking for an init.c, I believe. So what all do we have here? How about we just do this? We're going to include everything from devices and let's just include, okay, there's the entry and the start files. Okay, there's the init.c. And then let's also open up common.mk. Here, let's do it like this. Common.mk, encoding.h, entry.s, SiFive 1.h, start.s. Okay, and now let's take a look at init.c. I have an init.c, don't I? Did I not open an init.c? Oh, I see what I did. I opened header files, but not C files in that directory. So let's change this to say we want init.c. Let's also open up the link.lds. Might as well open the openocd.cfg. I don't know what that's for. And the platform.h. Okay, here we go. So this is the init file. Okay, here's the UART init. So she says do this after the GPIOs have been configured for UART. We haven't studied the GPIOs yet. We were just going to do that, but we got sidetracked. But we can see an example here. So there's these calls, and then there's these calls, and then they do the loop. So I think we just want to put it at the end here. So I'm going to do a volatile int, and like I say, we're making it volatile because this is a loop that doesn't do anything. The only thing it does is increment the variable I, so it would be trivial for the compiler to realize that nothing after the loop depends on the variable I. So in fact, it can determine that the loop really doesn't do anything. So it can just eliminate all that code. And so by saying it's volatile, the compiler isn't allowed to do that. So now we're just going to loop, and we're going to say, well, I is less than some big number. I think they did 10,000, and there's 100,000, so that should be good, right? So we're going to do plus plus I. And I think that should be good. Let's just make this a one-liner. While I++. There we go. Beautiful. So now, if I make software clean, and then make software, this should hopefully recompile the init stuff. It looks like it's being compiled right here. So that should have done our changes. Now, I preemptively put on my anti-static wristband before we started the stream. So I'm going to plug in my SiFive 1. All right, now let's connect to it. Well, actually, I don't know what our program is doing right now. Let me check what our program is doing. Okay, right now it's doing the search thing. So, yeah, we can print that. So I'll upload it to the board, connect to it, and I'll hit the reset button. So it looks like that was no good. Well, one thing we can try is a bigger loop. Let's say like int max, right? So I'll do a make software clean again just to make sure this gets rebuilt. Int max undeclared. What is the max of int then? Or maybe we just need to include a header. Can I just like man int max? int max is defined in stdint.h. So we're including stdint.h right here. Or wait, this is... No, this is init.c. Or wait, no, int max is defined in the limits.h. I see. So then, let's include limits. Now I'm not even getting the blinking lights. So what is the problem? I mean, I don't think it's just stuck in that busy loop. I don't think it should take that long to go through int max iterations of a loop. So I think what I want to do is just paste in the actual value of int max and see if that makes a difference. Oh wait, it is lighting up now, so it actually did just take that long to loop through int max. What do you know? So I'm going to let this run for a little bit and see if we get a good printout after all that time passes. I wonder how long that loop takes on an x86, like on my processor. Let's have a little fun while we wait. So I'm going to say volatile int I equals 0 while I++ is less than int max. Printf done. So that took like 5 seconds on my machine. And this is a quad-core Phenom 2. For those wondering. 3.4 gigahertz. Okay, so it did print properly. So let's set it to a number that's not quite that big, but big enough that it doesn't mess up for us. So what did I try? Like 100,000? How big is int max? Okay, it's got 3 commas in it. So let's add one more 0. That would be like 2 commas. All right, that seemed to work perfectly. So hopefully that will solve the problem I have with it giving us a little bit of trouble with output. So the next thing I want to do would be find the proper address. So she says the address should be 0x214EF. You mean the number int max popcorn? It should be FFFF. It shouldn't be 7F FF. I don't know why it would be 7. Or no, it would be 7FFF because we're talking about assigned integer popcorn. So if you go back and watch some of my videos, we got a pretty good intuition about how 2's complement works. And the number FF would be the smallest. That would be like int min. 7FFF would be int max. But yeah, if you look back to like the episode where I was doing like a ripple carry adder and stuff, and maybe like the episode after that, somewhere around there, we spent a lot of time like getting a good intuition about how 2's complement works. So if you're curious about that and want to develop a good intuition about it, there is some good content from my series. Just a little self-plug there. But yeah, 0xFFFF would be the int max if it were an unsigned integer. So 21FE4 is the address we want. All right, now that looks like a valid, this looks like a valid Unix timestamp. So let's put that in here and see what we get. Actually, that's even earlier. That's September of 2012. So that seems a little bit off. Let's check. Oh yeah, we should have read this more carefully. It says right here in the table that these are OTP offsets. But yeah, 21FE4. 1FE4 is the offset for the board ID. So where can we find in the documentation the start of the OTP? Okay, so this is, I'm looking at the E300 manual, I believe. Yeah. And chapter 2 has a memory map. So it talks about OTP control, but that's not what we're looking for, I don't think. So the memory address she listed, it says see E3 Coreplex manual. So let's take a look at the E3 Coreplex manual. Okay, so chapter 4 of this is the memory map that we were looking at to see the config string. So yeah, it says right here the base for OTP read ports is this right here, which is 20000. So I definitely have the address right. I think it's safe to say. So that would suggest that my board, the OTP was actually burnt in 2012. Yeah, that's correct, Miblo. It's F's all the way down. The intuition for it, just to recap from those previous episodes, is that what the number is it's 0 in the high bit, and then 1 in all the bits after that. Because in 2's complement, you count with like you invert it. So you count with zeros instead of ones. So like if the high bit is set, then it's the zeros that are like holding value. So the highest possible number you can have is when that high bit is set to 0 so that you're counting normally. So I'm going to report the value I have on the forums and ask why it's in 2012. That seems a little suspicious to me. Yeah, the 7 in hex, it means that it's a single bit is a single bit is off. So that's not what I want to quote. So I'm going to say the value I have at that address is, which would be sometime in 2012. So, I don't know who all watching has SiFive 1s. I think Miblo does. Would you be able to print it out, Miblo, and see what value you get for your board ID? Assuming you have the Freedom E SDK and all that. I think this is probably like working hours for Hossein, or sleeping hours or something. I don't know what time zone he's in, but he's usually around at night. So yeah, the code to test it is just you make a pointer to this address right here, and then you just print it. So just print the value from the pointer. Oh, okay, Miblo. That's going to take you like 30 minutes or some really long amount of time to compile. So just tell me on IRC sometime. But I am going to move on. So what else do we want to do today? I think we want to get back to the GPIO stuff. So first of all, let's take a look through the documents because I don't remember where we were. And we might be able to find stuff that we didn't last time because we weren't looking at the getting started guide, for example. So I don't think there's anything interesting about GPIO in that. I don't expect there to be anything in the risc-v manuals. I'll take a quick look, but I'm pretty sure this is platform-specific stuff. Yeah. And I'll take a quick look at this manual too. Alright, so I'm correct that this is all platform specific stuff that we're looking at. So let's look at the E300 manual. Alright, here we go, chapter 11. So the part that we got sidetracked on was right here. It said the SiFive GPIO controller is a peripheral device mapped in the internal memory map, discoverable in the configuration string. So that's not true for the SiFive 1, because the SiFive 1, we looked at the configuration string, and the only really interesting thing was it had an address offset to find more configuration information, and that pointed at nothing because nothing's been written there yet. So let's reread this opening paragraph. This chapter describes the operation of the GPIO on SiFive systems. The GPIO controller, discoverable in the config string, it is responsible for a low-level configuration of the actual GPIO pads on the device, which includes direction, pull-up, enable, and drive value, as well as selecting between various sources of the controls of these signals. The GPIO controller allows separate configuration of each of the N GPIO bits. Figure 11.1 shows the control structure of each pin. So here is that. Okay, so we've got that nice diagram here. And then we have this table showing address, name, description. These are GPIO register offsets. So atomic operations such as toggles are natively possible with the risc-v extension, which we have. The memory map of the GPIO control registers is shown in that table. The GPIO memory map has been designed to only require naturally aligned 32-bit memory accesses. Input and output. The same port register can be configured on a bitwise fashion to represent either input or outputs as set by the direction register. Oh, and this is the thing we took a note on, isn't it? So let me find that. Yeah, right here. So I took a note that the value is input and direction, or output and not direction. And that's what it's talking about in this document when it says tri-state value. The state depending on input, direction, and output. So those are three variables, so it's tri-state. So can represent either input and output as set by the direction register. Writing to the port register will update the bits regardless of the tri-state value. Reading the port register will return the written value. Reading the value register will return the actual value of the pin. And so this is the actual logic of it. And then interrupts. A single interrupt bit can be generated for each GPIO bit. The interrupt can be driven by rising or falling edges or by level values, and each can be enabled individually. Inputs are synchronized before being sampled by the interrupt logic, so the input pulse width must be long enough to be detected by the synchronization logic. To enable an interrupt, set the corresponding bit in the rise IE and or the fall IE to 1. If the corresponding bit in rise IP or fall IP is set, an interrupt pin will be raised. So if you set, for example, rise IE and rise IP, then on a rise, it will trigger an interrupt, I guess. And you can also do it on a fall or on a high or on a low. So those are for if you're level or edge triggered. So let's take a moment and Google level triggered and edge triggered. So a level triggered interrupt is an interrupt signaled by maintaining the interrupt line at a high or low level. So that's like what they were talking about, what Megan was talking about for the UART. It uses a level triggered model where they drive the line high or low, and based on that, it sees it as a start. So let me go back to that to show you what I'm talking about. So she said UART TX works with a single line which starts high. Then when the sender wants to send something, it pulls the line low to indicate a start bit. So normally you're always sending a signal on this line, basically. So you can think like in an actual circuit, right? You have a line of wire, and you can send a current through it. And so when you're sending a current, you have it high, and then when you lower the current, they use that to indicate a start bit. Whereas I'm guessing then edge triggered is where I guess it's where you just send like a pulse. And so it detects it either on the rise or on the fall of the pulse that you send when you do edge triggered. And yeah, it says a device wishing to signal a level triggered interrupt drives the interrupt request line to its active level, which is either high or low, and then it holds it at that level until it is serviced. So that's how level triggered works. And then edge triggered. An edge triggered interrupt is an interrupt signaled by a level transition on the interrupt line. Either a falling edge, which is high to low, or a rising edge, which is low to high. So a device wishing to signal an interrupt drives a pulse onto the line and then releases the line to its inactive state. If the pulse is too short to be detected by pulled I/O, then special hardware may be required to detect the edge. So those are the two types there. And that's a kind of thing that you encounter when you're doing circuitry as well. Like I remember dealing with that sort of thing a little bit back when I was making circuits in Minecraft. So let's go back to the documentation here. Whoops. Okay, it was this one right here. So once the interrupt is pending, it will remain set until a 1 is written to the IP register at that bit. The interrupt pins may be routed to the PLIC or directly to local interrupts. So once the interrupt is pending, it will remain set until a 1 is written to the IP register. I thought you wrote a 1 to the IP register to enable an interrupt. I mean, you do that for the IE, but I thought you did in the IP as well. So, I mean, the IP, it stands for interrupt pending. And we're saying if the corresponding bit in one of the IP registers is set, an interrupt pin will be raised. And here it's saying once the interrupt is pending, it will remain set until a 1 is written to the IP register. So I'm not sure if I fully follow that. I'm a little bit confused about when you write to the IP register. But I think we'll figure that out later as we mess with this more. So let's keep reading. Internal pull-ups. When configured as inputs, each pin has an internal pull-up, which can be enabled by software. At reset, all pins are set as inputs and pull-ups are disabled. So I don't know what an internal pull-up means. I think that's some circuitry lingo that I'm not familiar with. Define GPIO pull-up. So what is a pull-up resistor? What does it do and why is it needed? Often it is useful to steer an input pin to a known state if no input is present. This can be done by adding a pull-up resistor or a pull-down resistor. So a pull-up will make sure the pin is up without taking in too much current. So a gate has three possible states: on, off, and floating. The floating state is not useful to us, so you use a pull up or pull down to eliminate the floating state. And there's a comment here that says, technically floating is not a logical state, but a loose technical term used to describe that is unconnected and may receive random combinations of high-low caused by static discharge noise generated by nearby objects. Okay, so that's pretty technical. Why is that mentioned in GPIO documentation then? So it says they have internal pull-up, which can be enabled by software. At reset, all pins are set as inputs, and pull-ups are disabled. So I take it we're talking about pull-up resistors to make sure that the pin isn't in a in-between state where you get garbage. I don't know why you'd want to enable or disable that in software. So I'm not totally following the purpose of that, but I'm sure as we mess with GPIO, we will encounter more of this stuff. So drive strength. When configured as output, each pin has a software controllable drive strength. And again, I'm not familiar with exactly what drive strength involves, but we will find out. Output inversion. When configured as an output, either software or IOF controlled, the software writable out exclusive OR register is combined with the output to invert it. So that one's pretty straightforward, at least. And then we have hardware I/O functions, which is IOF. Okay, so that's what they're talking about when they say IOF. Hardware I/O functions. Each GPIO pin can implement up to 2 hardware-driven functions enabled with the IOF EN register. Which IOF is used is selected with the IOF select register. When a pin is set to perform an IOF, it is possible that the software register's port, output EN, pull-ups, DS, input EN may not be used to control the pin directly. Rather, the pins may be controlled by hardware driving the IOF. Which functionalities are controlled by the IOF and which are controlled by the software registers are fixed in the hardware on a per IOF basis. Those that are not controlled by the hardware continue to be controlled by the software registers. If there is no IOF X for a pin configured with IOF X, the pin reverts to full software control. So that was a ton of information that I don't fully understand, but that is part of the process. We're in the sponge mode of soaking in all the information. And I think we're out of time for today as well. So thank you everyone who tuned in today. And thank you everyone who watches on the YouTube archive, which is available at risky.tv. And you can follow me on Twitter at HMN_risky to get updates about this series. So I will see you next time, and stay risky, everybody.